at TVIW. I don't think Professor Lubin needs an introduction, but I'll try anyway. He's a professor at UC Santa Barbara, got his doctorate in physics at Berkeley, and is working on interstellar propulsion with external photon fuel source, so to speak. Please take it away.
The takeaway in this one is leave your power source at home. So do leave home without it. So I want to go through a few things with you because this truly has a transformational capability in a large number of areas, of which going to relativistic speeds is only one of them and probably not the most important. So I'd like to emphasize that to you. The other thing is if you look around the facility we're in, we're very close to Y12, which was both the diffusion and the electromagnetic separation of uranium for the nuclear weapons program during World War II, amongst other things. If you look at the start of Y12 was 1943, approximately January, and by the end of 1944, they had already produced the uranium-235 needed for testing and ultimate use in the little boy weapon. It's 2 years. If you look at John Kennedy's speech on September 12, 1962, to the moon landing in July, it was 6 years, 9 months. So that 6 and 9, if you want to think of that, are the only two numbers that are mirror of each other. So if that helps you visualize 6 years, 9 months to do something revolutionary, and 2 years to do other things revolutionary in the place that you're standing in. So things can be done if there's a will, and that's part of the way forward, is to actually have a will. Unfortunately, we haven't always had that will. Okay, if you have a will to go to sleep at night and can't do it, please read one of my 50 papers. They will definitely put you to sleep. They always do. I've been told by a number of people, no, I never read your papers because they're too long and too technical. If you want to look at some pictures, look at the one called the Roadmap to Interstellar Flight, which outlines the basic technology. Thanks to Jason and NASA, we now have 3 total NASA programs between us and our collaborators, all in phase 2. And that's been an incredible boost, so I really want to thank you, Jason and NASA, for really going on a limb and supporting something that was really quite far out there. In fact, I think the statement I saw in the reviews was, this is the closest thing to science fiction that we've funded, or something like that. I can't remember, some very interesting term. Also, this is NASA's program that we're funded for that started what you've heard of as a breakthrough star shot, not the other way around. Okay, so we call the Starlight now, just to give it a little fancier name, and I would call it the path to long-term strategic transformation. And indeed, it is long-term strategic transformation. So long-term program goals are to develop directed energy propulsion, i.e. standoff propulsion, standoff power for high-speed applications. And I'll show you 2 different variants of it. It would enable, if brought to completion, the first relativistic flight program, i.e. it would enable humanity's first interstellar missions, but it does much, much more than that. One of the things it does is enable extremely rapid interplanetary missions, and I'll explain that in detail in a bit. It also enables you to be empowered for a variety of applications, including ultra-high ISP ion engine applications. We have a program with JPL, John Brophy's group, looking at ISP 60,000 lithium-ion engines. Also enables being empowered for a variety of other space applications. And the basic issue for what we're doing now is that chemistry hasn't changed, and I'll show you examples of that from literally going back to the start of Y12, quite literally. And that's because chemistry has a bond energy of about 1 electron volt, which gives you an efficiency for the engine of about 10 to the minus 10. So chemistry and nuclear, I will show you, cannot get you to relativistic speeds. And I'll go into that in some detail. However, unlike chemistry or even nuclear, photonics, like electronics, is exponentially growing with a doubling time of about 18 months. Coincidentally, both electronics and photonics have about the same doubling time. It's also the case that photonics, the use and manipulation of light, has reached the feasibility point for propulsion, and I will try to argue carefully with you. This is also a very incremental and both an evolutionary program as well as a revolutionary program. It's not all or nothing. It has a very reasoned and cost-effective roadmap going forward, so you don't have to spend $1 billion to buy into the program. And you can do it in your laboratory. And it also is the only technology I know of that is completely scale-free. We can use it for things at the gram level and at the 1,000-ton level. And that's totally different than any other technology that I'm aware of. Even antimatter cannot do that because of the containment masses required. It also leverages enormous capabilities in other markets that feed it, namely the US and worldwide commercial photonics market and electronics, which has a lot of implications. Okay, so this is really a great takeaway. Here's a 1943 V2 rocket engine. Here's the SLS test firing. Here's SpaceX Falcon Heavy. ISP 215 with LOX and alcohol. ISP of around 350 or so with LOX and kerosene. ISP 450, LOX and hydrogen. You're not going to do any better. If you put hydrogen into the V2, you would have gotten almost identical performance to the SLS. Never changed, never will. Okay, so that's 75 years. Here's 1943, the year that Y2 was formed. Here's the ENIAC, 500 flops. Here's 99, a teraflop, 1 billion times more performance, obviously much smaller, trillion times less power per flop, and 1,000 trillion times less mass per flop. Okay, that's a revolutionary and exponential technology. This is not and cannot be. Okay, I'll skip this. This is just how fast we've gone. In the laboratory, we get up to within 1 meter per second the speed of light with accelerators. Here's where we are way down here, okay, on a log scale. This is where we believe we can fill in the gap with directed energy. A good takeaway from this is that if you took all the mass in the universe, all of it, and made your payload a single proton, you could not get to relativistic speeds. It just doesn't work. Same is true for existing ion engines. You cannot get to relativistic speed with existing ion engines. Sometimes I get asked the question, why don't you just use an accelerator instead of an ion engine and get to within 1 meter per second as you do for accelerators in the laboratory? And I tell them, great, you just invented a light bulb because the physics is the same. So that doesn't work. Okay, so here's the propulsion landscape of everything I know about. Here's directed energy, either used directly on a reflector, such as my laser pointer, or going through a photoconverter to drive an ion engine, which I'll talk about. Here's misdirected energy, known as the sun. You can do the same thing with a solar sail or photovoltaics on an ion engine like the Dawn mission. Here's fission, fusion, antimatter, if you could do it, going to a generator, going to an ion engine. So we just heard some talks on nuclear electric. Here's fission, fusion, antimatter with reactor products. And here's chemical or nuclear thermal going to propellant. Okay. Okay, so there's two basic modes of operation here. One's what we call the direct drive mode, or DDM. Here's where you use photon momentum exchange, just bounce photons off the reflector. You have no fuel on board. This is the lowest system mass. There's no internal engine. Scalable to any payload mass. No other technology, as I said, can offer this. It's the only known solution to relativistic flight, with the one exception of antimatter. Can also, in theory, get to relativistic flight if we could figure out how to contain it with low secondary mass. Requires high power, higher power than indirect mode due to the very high ISP. It has an ISP of 30 million. Sounds great, but it's not really what you want for some applications. The second mode is indirect drive, where you reconvert to electrical power on the spacecraft to drive an ion engine. So we now have a program in this as well as in this. You use this mode for large mass, slower missions. You cannot get to relativistic speeds. You can stop and go into orbital insertion, at least out to Jupiter with some of our programs, at least on paper. Scalable, again, to any payload mass, from grams to as large as you want, greater than 100 tons. Not for relativistic flight, so don't confuse the two, please. And we'll talk about specifics. Okay, so what about nuclear? We've heard a number of talks. Nuclear is fantastic for a number of applications, but if you try to build a fusion reactor, fission really is not viable at all, but if you try to, for relativistic missions, if you try to build a fusion reactor for relativistic missions, just spit out the products using something like inertial confinement fusion. If you go through the math, it doesn't work. Okay, people have tried on paper, and then when you look at it in detail, it just doesn't work. And actually, for those of you in the weapons industry, if you look at the most efficient thermonuclear weapon, which is the Russian Tsar Bomba case, which is about 5 megatons per ton, you get an engine efficiency of about 0.02%. Okay, and it's that which really kills you. Okay, so if you line up all the fusion reactions, which I'm putting into a paper, it's going to come out. You can't get there. Okay, I know people want to get there, but it just doesn't work. At least for time scales which are, be careful here, for time scales which are, say, less than a human lifetime. If you want to wait 100,000 years, we already have a mission that'll get to the stars, namely Voyager. We're done. Okay, but that's not what we want in general. So in the direct drive mode, I'm using momentum transfer. It's not just for these little tiny spacecraft that people kind of stereotype us in. Here's a gram, here's a kilogram, here's a 100-kilogram case. They can all get to relativistic speeds, where we define relativistic speeds as being greater than a few percent the speed of light. It just depends on how large the array, the phased array that you build is, which I'll talk about in a moment, and how much power you supply. So there's no upper limit in this case. It's just a money and a technological development issue. I'm going to show you a lot of laboratory data at the end that we've been working on. There's lots of targets nearby. If you're interested in relativistic, it's only one of the things you can do here, but within 20 light years is about 150 stellar systems. This is just showing you that photonics is indeed an exponential technology. This is power out of a single mode fiber versus year for the last 25 years. It's been growing exponentially. I did a fun calculation as I was listening to the talks this morning. The power out of a single mode fiber that we have today is about 100 terawatts per square meter. That's roughly the equivalent of the flux from the highest power point in a 1 megaton explosion 1,000 meters away from the explosion. So, and we run continuously. And whereas a 1 megaton detonation is over pretty quickly. Okay, somehow we've interested Congress in this, which I hope this actually stimulates NASA, which it seems to have had some effect in. And I'm hoping that Congress will follow through by putting some money in rather than just telling NASA to do it. I hope they follow through with some money for NASA to do it. And in the report, they actually talk about the NIAC program, which is the one that NIAC funded for us. Okay, so how do you do it? How do you build this gigantic photon source? Actually, its power is not the problem. Actually, we can generate as much power as you want. It's phasing, which is the issue. So it's basically like a parallel processing computer. The way you make a supercomputer is take a lot of i7s or Xeons, actually was a better choice, and stack them together, and then you have a supercomputer. You synchronize them. Well, we take a bunch of laser amplifiers, which are about the size of your hand, and put out of order the same as an LED light bulb in your house, of order 10 to 100 watts, and you have to phase lock them. It's that phasing which is the tricky part. It's a synthesized system. So it's called a MOPA technology, or master oscillator power amplifier. This is used a lot in phased array radar systems, not used as much in photonics, which is what we're working on. The system is bidirectional, so the same system used to power your way out also is used for receiving data on the way back. So you now have an enormous receiver for long-range laser comm. So if you're interested in that, we have a long paper that I'll show you at the end. And we literally have 50 papers, so if you want to get bored, knock yourself out on our website. It's also, this is a case where you can test things inside the atmosphere. It turns out the atmosphere has about 95% transmission at 1 micron, which is, our amplifiers are currently optimized for 1.06 microns. It's just currently where the technological sweet spot is. We run a high altitude site at the University of California, which is at 4 kilometers, about the same as Mauna Kea. The transmission is about 95% on a clear day. So you can actually test this inside the Earth's atmosphere. Not necessarily where you deploy it in the long run, but it's interesting you can test it on the ground, which means it's much lower cost to begin testing. And no, you don't blow airplanes out of the sky, okay, although you could, but we won't. Okay, I think a better place in the long run is to put it on the moon, maybe even the backside, so you don't worry about it being pointed back at the Earth. The moon's nice because it has a nice vacuum pump around it, known as space. And there are ways to imagine such a system. It's not where you start, but certainly something to think about for the long run. So we have some ideas about doing that. So I think if we are going to go to the stars, the way we're going to do it is not with people on board to begin with at all. I'm not particularly interested in sending people to stars. I think we're just way too high maintenance and not the appropriate biological species. But robotics are great. And I think we'll go out on a beam of light because that, I think, is the only viable technology forward at the moment. And the laser is not on for long periods of time. It only takes about 100 seconds to shoot out small payloads and longer for heavier payloads. So no, the laser is not on for multiple years. And then in the scenarios we've been looking at for NIAC, it takes about 20 years to get to the nearby stars. Okay, so one system, you build basically one launcher, and then you can launch an unlimited number of payloads of a variety of types. Basically a variety of masses, any mass from basically gram scale to 100 tons or more. There's no upper limit to either. This is for high power, high speed, low mass missions. For example, the time to 1 AU is, it takes about 8 hours to get a kilogram out to 1 AU and stop it at 1 AU. It takes about 3 days to get 100 kilograms out. And in the far, far future, I wasn't going to put this up, I thought I'd just mention you for fun. This system has no upper limit. In theory, you could send humans to Mars in 3 days and stop them. They don't have to pay extra for that. And you go out at 1G, so there's no weightlessness, and you're just gone for 3 days. But I have to explain why this is not something that we're focused on. But in this technology, that's a natural evolution to it. In the moon, by the way, it takes about an hour to get a kilogram to the moon. This is in the direct drive mode. In the indirect drive mode, we have a path, I believe, to Mars in a month. So those of you that may have studied NEP or nuclear thermal, Mars in a month sounds like a dream, and it is. And that's because we start today at alphas of 1. We already are at alpha 1. Our goal is alpha of 0.1. And it's only because we're not carrying a reactor with us, which is the only suitable thing for these kinds of missions because the power levels are high enough. And the alpha in a reactor itself, as we just heard, currently today, well, the ones that are actually built are much greater than 10, but one can imagine 10, as we just heard, 8.5, with a goal of alpha of 1. Okay, our goal is alpha 0.1. We're already at alpha of 1 today. Okay, so this is actually quite exciting to think about. This is not pie in the sky. We can show you orbital trajectories where this is possible. It's not our current focus, except in something that we're putting together as a proposal. But, okay, so we're building things in the lab. I'm going to show you a bunch of data in the moment. This is actually not quite to scale. The full system is large. I mean, you're talking kilometer scale for the full one. This is one segment, one piece of that puzzle, which is a mosaic array. And the panels are hexagonal, just like this, with close-packed circular lenses. These lenses are a bit smaller than you would use. We'd use ones that are about 10 centimeters for operating inside the atmosphere to match the isoplanatic patch size on the atmosphere. Okay, so now I'm going to show you some data, because we actually build things in the lab. Nice thing about this kind of program is you can actually build things. So I'm going to show you some really interesting data. So we built what's called a Mach-Zehnder interferometer, which is basically a fancy name for a two-element phased array. And we developed an ultra-high-speed data acquisition system to go around it. So it doesn't mean much to you, lots of fibers and modulators and things. But it's basically a real two-element long baseline array. Okay, and you put your baseline right here. Okay, so one of the tricks to this program is how do you phase lock the system so it maintains a fully diffraction-limited synthesized array. And so we have a whole scheme for cascaded branching, which we're working on with our collaborators at Lincoln Lab. By the way, in the first slide, I didn't mention, in addition to NASA funding us, we have funding from the Gladys W. Technology Fund, Gladys and Emmett W. Technology Fund, and then Breakthrough Foundations is starting to put in some funding as well as NASA. Okay, so this is actually one of the hard parts of the program. Getting power is not the hard part because it's a parallel system. Getting phasing is the hard part. So here's a 11-kilometer array baseline. And here is the RMS error. This is how well we can do as a function of baseline in meters. So here's 11 kilometers out here. So this is larger than the largest system that we currently envision. And this is the RMS error. The blue is what you want to focus on because this is a balanced system, which is the only way we would build a system. It has approximately 45 milliradians of error, so divide by 2 pi to get milliwaves, so about 7 milliwaves. So we're down to an error of 10 nanometers, which is lambda over 100. So for those of you who might know something about optics, you typically want to get to better than lambda over 10 to get a high Strehl ratio. We're at lambda over 100 already. And so it's vastly better than we need. I didn't think we'd do this well, but we have now done this well. So our actual system noise is less than 1 nanometer, which is approximately the size of an atom. So we've done better than I thought we'd do. This data was, by the way, taken last week. We can synthesize any beam shape because we're essentially a Fourier transform aperture. So this is a spot size of a fully synthesized beam with a diffraction limit, and here we spread it out just for fun, just to see what we could do. There's nothing particular here except to tell you we can make arbitrary beam shapes for a variety of mission parameters. We can put nulls in the middle, we can put all kinds of interesting peaks, we can spread them out, narrow them. This is what the beam pattern looks like. It has some side lobes on it, but they're actually not too bad. What's neat is our students have developed a algorithm technique that we can run on gaming GPUs. So we can now, we've synthesized already a 1 million element array, and this technology can go up to, we plan to go to 1 billion elements just for fun. We're also adding atmospheric perturbations for testing ground-based simulations. Okay, so thanks to gamers, we're actually able to do things faster than I thought we would. Now we've started to build our own amplifiers because there wasn't anything commercially available that did what we want. So we have a bunch of students and researchers who are really good at photonics at UCSB. We're part of the National American Institute of Manufacturing and Photonics, the AIM Institute, which is a national, the government, national labs, and industry. It's a multi-$100-million program. I'm just the recipient of this. The West Coast leader is one of the guys in our electronics and computational engineering department. Okay, so we've built now our power amplifiers, and they don't look all that exotic. We're just testing them on the bench here, which is nice because you can actually test this stuff. But we've already achieved more than 40% efficiency. That's electricity in to photons out, actually 42%, with a greater than 30-kilometer coherence length, which is good enough. This is already good enough for our purposes. It's not cheap enough for our purposes, but it's good enough in terms of performance. Okay, so here's what the actual efficiency curve looks like. This is all done, built in our lab. Okay, so 42% efficiency. But the real path forward for economic reasons and for other reasons having to do with just reducing the complexity is to put things on wafers and then scale the wafers together. So this is work in directed energy photonic wafer scale integration. So this is 3.5 material on silicon. So this is work done at Santa Barbara, built in the clean rooms at Santa Barbara by John Bauer's group. Basically, this is a large number of elements on a wafer, and then these wafers get cascaded. So there's a lot of industrial interest amongst some of our aerospace industries who are nearby in the same technology that we're developing here. This is a lot of applications, not only for industry, but for DoD applications. So I won't dwell too much. Here's a physical chip that was made from that process that works. Some people want to understand if you're going to put so much power on a reflector, aren't you going to vaporize it, blow it apart, et cetera? And the answer is that the amount of pressure is similar to what this thing puts out. Does anyone recognize this? It's a CPAP machine. That's what blows your lungs up to keep you breathing at night. So the amount of pressure here is roughly what your lungs can generate. That's the full pressure of propelling something to the stars. In the worst case is actually the smallest mass, which is the highest pressure. So here's a 500 nanometer film that our students are testing. You can actually see the interference pattern in the film because it's so thin. Laser comm, there's a 50-page paper if you want to read it, knock yourself out. It works, it's just hard. We have started building wafer scale spacecraft at UCSB. This is, again, not the only thing you can do, but just for fun, we're doing it because it's something students can actually do. This is about 1 trillion transistors on it if we were to populate it, which we haven't done yet, but it would hold 1 trillion transistors. It's the size of a hand, weighs roughly a gram. It would be really interesting to populate the solar system with these to have low-cost missions to take pictures, to put spectrometers on board. You can do all kinds of things with 1 trillion transistors. Just imagine, 1 trillion transistors, by the way, is roughly 1,000 modern CPUs on a wafer, and that's with today's technology. Okay, just to keep this in perspective, humanity is now at the point where we're developing a technology that is the brightest, what we call spectral energy distribution, or SED, in the universe. This is the brightest thing in the universe, and it is visible across the entire horizon. We've done simulations. You can read here's another 50-page paper in the archives, just called The Search for Directed Intelligence. The idea is, if we have developed this technology, is there any other civilization in the universe? So just so that you might think about something when you look out the sky tonight, in every square degree, there are roughly 1 billion planets that you're looking at in every square degree. So when you look up at the sky at night, you're seeing roughly 1 billion trillion planets in your eye, in your field of view of your eyes. Of course, you don't detect them all because your eyes aren't that sensitive, but the numbers are staggering. And so you might want to think about it. So we have a search going on at the moment, but not the purpose of this talk. Okay, so conclusion. So directed energy actually offers a path to propulsion transformation for basically all payload masses. I wouldn't say all payloads, but for all payload masses, from tiny to large, from CubeSat and below, all the way up to BFR class missions, going to Mars, with the same technology. This one technology is scalable across all ranges of masses. You build one launcher, you can launch all masses. Lower mass goes faster. It's evolutionary. We're already starting in the laboratory, and you can build up from there. So we have a roadmap. If you read our roadmap paper, you see we start in the lab with 1 meter, then we go to 10 meters and kind of work our way up. And each of them has an immediate application. Even a 1 meter has immediate application for space use. 10 meter has some very dramatic applications for space use. It allows rapid prototyping and short-term milestones. So you can feed back the system very quickly, which is why we'd like to push this very rapidly, because it doesn't take a huge buy-in to begin this program. You can actually start pretty cost-effectively. Okay, so it's also the only known path to ultra-high-speed spacecraft. I mean, ultra-high-speed being relativistic, but it's also a path to getting to places like Mars very rapidly. It's the only known path to interstellar flight, I would claim. Lots of other applications, from molecular composition analysis to planetary defense to solar system-wide LiDAR, ultra-long-range laser comm, space debris mitigation, et cetera. Lots of long-range power beaming applications that we have papers on, proposals, grants, and a number of other things on. You can also build things in laboratory. So we've been talking with some of our colleagues in some of the accelerator labs about building something like this. It leverages the enormous exponential growth in the photonics industry, which is a many billion-dollar per year industry. It's tens of billions of dollars per year spent in photonics. Okay, it requires a dedicated program. So I think this is where we have to think about this. So what I hope to come out of a discussion with you today is, how do you make a system like this go? How do you make a program like this go? You need the buy-in of NASA, but you need the buy-in of a lot of people. It'd be good to have the buy-in of DARPA, of DOE, of lots of people within the government, as well as the private sector. And if we don't do it, someone else is going to do it. So in my opinion, the US should really lead in this transformation. I think this is a perfect place to think about this, because where we're standing today was one of the places that was historic in the ability for the United States to lead a transformation in nuclear power. The last thing I want to tell you is, look around the room. Just look around the room. Who do you see here? Unfortunately, you don't see what you really want to see here, which is, where are the next generation? There are some here, but it's not the majority. Why are we here and they are not? Maybe they didn't have travel funds. I don't think it's just that. I think we have to think hard about this. In our group, in the last 5 years, we've had more than 100 students doing research in our lab. They love this stuff. It's so much fun for them to blow holes through things. There's something about physics students and destroying things that just, it's just fundamental, which is one of the reasons why Y12 exists, by the way. I grew up in Berkeley at LBL and I was part of the Louis Alvarez group, and Edward Teller used to come around. And I mean, I know this group, right? Physicists love to do things that are interesting. So it engages the public imagination. We have a path where we can engage a large number of people and gather a large interest. These are just some of the students that are involved. And it's the young people. I'm not going to be around when this thing goes off, but young people could push this forward. So I will stop there, and I'd love to engage with you later if you have questions.